Hello, are you able to see the slides?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Okay. Welcome to Department of Chemical Engineering, Banastali Vidyapeeth. We are on CHT 305 Chemical Technology lecture number 10. In the lectures till now, we have seen the basics of process, uh, futures of the chemical industry. When we focus on the generation of hydrogen, what are the various ways by which hydrogen can be produced, because hydrogen is going to be the fuel of the future. There we ended. Of course, hydrogen becomes the fuel, future fuel, when it combines with oxygen to form water. And where do you get the oxygen from? You get the oxygen from air. Air contains oxygen and nitrogen. But the story starts there for us. We come to exciting field of chemical engineering. What is cryogenics? Cryogenics is the science that addresses the production, effects, and maintenance of very low temperatures. Cryogenics is not no refrigerator in the house. Yes, but we are talking further, very low, minus 173, etc. It also includes the study of properties of materials at cryogenic temperatures. Remember that many materials are said to become superconductors under cryogenic condition, because the resistance becomes so low, they become superconductors. So cryogenics is an exciting field, right? And that's where we are coming into today's focus on the lecture. And this application of the science takes the form of a classic enabling technology that over the years has evolved from its origin in air separation. The starting point of cryogenics is from air separation and liquefaction of gases into a wide range of applications involving the use of cryogenic fluids and increasingly sophisticated low temperature refrigerators. Remember, the liquefied natural gas we use as fuel is also based on liquefaction of gases. So cryogenic systems now find application in fields as diverse as food freezing, medicine, space exploration, transport, and storage of liquefied natural gas, that is LNG, energy and defense, as well as in the wide-ranging applications of superconductivity. So cryogenics is just not about feeling cold, but doing a whole lot of new things. According to the laws of thermodynamics, there exists a limit to the lowest temperature that can be achieved, which is known as absolute zero. Over the years, in terms of the Kelvin scale, the cryogenic region is often considered to be that below approximately 120 K, that is minus 153 degrees C. That 2 is a reference. Okay. The most common methods of producing cryogenic temperatures almost always utilize the compression and expansion of gases, thus making these gases valuable commodities in the science and application of cryogenics. So, there is a compression and expansion of gases. Just put it into your head. We will see more of it soon. Gases such as methane, argon, oxygen, carbon dioxide can all be supplied as cryogenic liquids. That is, cryogenic liquid is not limited only to liquid nitrogen and liquid oxygen. Well, it can be methane, argon, carbon dioxide also. Cryogenic cooling of instruments and material samples is usually achieved using liquid helium or liquid nitrogen. So many instruments, they have to have low temperature cooling, cryogenic cooling, and material samples. For example, many biological materials, they are all kept under very low temperatures so that they remain protected. They are such cooling, cryogenic cooling is achieved using liquid helium or liquid nitrogen. Helium. Remember, hydrogen is the most abundant source in Earth as well as the universe. 75% of the universe is hydrogen. And the next most abundant element is helium. You know how hydrogen becomes helium. You know how the sun works. We are not getting into it. Helium is not available infinite. Right? This finite resource on Earth and growing scientific, medical, and high-tech demand for helium has been tempered by a doubling of prices. Helium prices have been doubling over the last 5 years. Helium is the second most common element in the universe, but it is comparatively rare on Earth. Not available here and there. It also fulfills a surprising role in everything from space exploration to quantum computing. So helium plays a role for space exploration as well as for quantum computing. Helium is the only element on the planet that is completely non-renewable resource. Non-renewable, remember. On Earth, helium is generated deep underground through the natural radioactive decay of elements such as uranium and thorium. It takes many, many millennia to make the helium that is here on Earth. So very small quantities of helium is produced naturally, that is natural radioactive decay of uranium, thorium, and the world's helium supply is located in just a handful of countries, not in all the countries. The United States of America, Algeria, and Qatar. These are the three countries which are bestowed with natural source of helium. All others have no access to it, you have to buy it. Okay. Liquid nitrogen. So, helium is not available. Then my next choice is liquid nitrogen. Liquid nitrogen is the most commonly used element in cryogenics and is legally purchasable around the world. Right? So there is no law which prohibits the production and generation and sale of liquid nitrogen. Now, nitrogen is not available as a free raw material. It is available in air as a mixture with oxygen. Now, typical composition of air reads like this: 78% nitrogen, 21% oxygen. You have used this roughly in all calculations. Remember, we have used 79% nitrogen and 29 oxygen in all the chemical process calculations for material energy balance. But in 79 nitrogen, we included the argon and other rare gases, but correct split of air would be 78% nitrogen, 21% oxygen, 0.93 argon, and 0.07 carbon dioxide, neon, helium, methane, hydrogen, krypton, hydrogen has got repeated twice, xenon, nitrous oxide, nitrogen dioxide, small quantities, right? But they are not ignorable. Remember, argon, neon, krypton, xenon, all the rare gases along with helium, they are there, right? In addition, small quantities of water, right? Carbon dioxide, methane, some hydrogen, nitrous oxide, nitrogen dioxide, etc. are there. Now just look at the properties of oxygen, nitrogen, argon, because they are the three major: nitrogen, oxygen, argon. Remember, why are we studying it? Because I want to separate from air, say a nitrogen or oxygen or argon. I have to use some property to exploit. Okay, let's look at oxygen molecular weight 32, nitrogen molecular weight 28, argon molecular weight 40. Oh, well, molecular weights are different, but I don't have many established mechanisms by which I can separate a mixture of chemicals based on molecular weight. Of course, you have the membranes and uh, the ones, molecular sieves, etc. But they are still not, able to exploit it in a commercial way for a clean separation of oxygen, nitrogen, and argon. Right? So exploiting molecular weight is theoretically is possible, practically has a long way to go. Then comes melting point. Okay. Melting point, see, minus 218, minus 210 for nitrogen, for argon, minus 186. By the way, like argon melting point lies between, different, right? It is on the, if you put them in descending order, you will have a different picture as compared to the molecular weight. Okay, but these are far low temperatures. Look at the boiling point. Oxygen minus 183, nitrogen minus 195, argon minus 185. So if you compare the boiling point and melting point, the boiling points of oxygen, nitrogen are far lower than that of the oxygen and nitrogen. Remember, oxygen and nitrogen, if I have to use melting point as the property difference for exploitation, I have to achieve more excursion in lower temperature. I have to go to minus 210, minus 218 to separate oxygen and nitrogen, whereas I have to reach only minus 183 and minus 195. Remember, minus 183, minus 195 is relatively warmer as compared to minus 218 and minus 210. So, if I have to go lower and lower, the cost goes higher and higher, right? So, as a thumb rule, we avoid excursion below atmospheric temperature and pressure, but wherever possible, look like, we try to be on the better side. Okay, so exploitation of boiling point is going to be the main criteria for separating the mixture of air, oxygen, nitrogen, argon into oxygen, nitrogen, and argon. How do I go about separation? Just I am reading out the steps. The air may contain dust, natural, right? So I need to put a filter by which the dust can be removed. So air filtration done. Then I compress the air to 6 atmosphere pressure, because remember, compression and expansion is the strategy we use. We had just mentioned that, right? Utilize the compression and expansion of gases. So we are going to work on the compression and expansion. Ambient air is compressed to 6 bar, 6 atmospheres. Purification of for removal of water and carbon dioxide, because air contains small quantities of water and carbon dioxide, and I have to remove it, otherwise water will form ice and CO2 will form dry ice at low temperatures. So I have to get rid of the water and CO2. I'll have to do this. So first dust removal, compression, then removal of water and carbon dioxide. Then I cool down my air to 173 degrees, which is close to the liquefaction point. And then I do a distillation in 2 columns. First column operating at 6 bar, minus 173 degrees C for oxygen removal. Second column, just outlining the steps. All right, I am not explaining the concept. Right. So second column is 1.4 bar and minus 193 degrees C for nitrogen removal. This is our way of working. Now, I told you that the way by which, why we do compression, expansion, and how we operate, bringing this cooling effect, all this is based on thermodynamics. And you have studied some thermodynamics in your first year. Of course, you have studied some more in chemical engineering, thermodynamics also. So basic concepts are known to you, and the person I wanted an expert who could explain the thermodynamics behind the separation of air into oxygen and nitrogen. Who else I can get other than Professor Satish Shukla, well known to you, Right, he holds a PhD, is an alumni of IIT Kharagpur. His areas of technical expertise and interest include multi-phase flow, mineral beneficiation, rheology, and thermodynamics. So here comes the surprise. The air separation and exploitation of thermodynamics. I'll request Professor Shukla to take over and explain to you. Okay, welcome, Professor Shukla.
Hello everyone, I am Dr. Satish Shukla. I welcome you all. I hope you can hear me clearly. Hello?
Yes, sir.
Okay.
Yes, sir.
Okay, welcome everyone. Now,
Check are they able to hear and not?
now you have some idea. Now you have some idea about uh, what are the contaminants present in the air. So this is a very important slide which Dr. Natarajan has explained. Now, when we do the separation of the gases, mean either like Dr. Natarajan said, either we should have some membranes or separation type process, but membranes, so fine membranes to separate two or more gases, right now these are not very feasible option. Okay, there are no such membranes which can separate two gases. So what, how we can separate? If you see in this slide, and the right hand side, you can see there is a point written boiling point, which means when we compress gas and if we decrease the temperature, we can achieve such a temperature a gas can cool. A gas will become in liquid phase, and that's how we can separate. But if we are going by doing liquefaction and by that if we try to achieve the separation, we need to understand how we will liquefy the gas. Okay, so if we want to liquefy some gases, that means we have to understand the cryogenics of air separation. In other words, cryogenics. And if you want to understand the cryogenics, we first need to understand thermodynamics. Okay, so only thermodynamics can tell us how we can liquefy some gases. So I will going try to explain.
This is the point.
So first knowledge you need, that is basic thermodynamics, concept of thermodynamics, which you have gone and undergone. I will explain them in a bit. Second, not only just knowledge of this thermodynamics, you also need to see other factors. What are the design constants? We will go further in details in a few other slides. So why it is required, or what are the design basis? Next is basic cycle steps, means in your flow sheet, how you will, what process will be involved? Will there be a heat exchange? Will there be a distillation? Will there be a compression? Okay, so you have to identify your basic cycle steps. Okay, to minimize your cost, operating cost, and other things. So, and last, fundamental concept means, of course, without these fundamental concepts like mass balance, yeah, mass balance, pressure balance, energy balance, and calculation on compressor. So let us go to the next slide so you can understand better. Now, basic thermodynamics. You need to understand the four laws of thermodynamics, but I believe we are already aware of it. So, object at the same temperature. This is called zeroth law of conservation of. First, second is conservation of energy. Third, next one is entropy. I believe you have gone all those with. You have gone with all these law in your first year course. So I'm moving ahead. Now, basic thermodynamics property diagram, you also need to understand to make a plant design. You also need to understand what is the pressure, temperature, volume, temperature. So these are all called, these kind of graphs, these are called property diagram, which helps in design. Some, these are different type of thermodynamic process which you have already studied: adiabatic, isochoric, isothermal, isenthalpic. Now, Design constants. Design constant means first you need to identify identify what are the variables which you need to observe. For example, whether the product will be gaseous or whether the product will be liquid, how much purity of the product is acceptable, how much pressure we need of the or how much temperature of the product we need. Okay, these all are the variables which you need to decide in advance so that you can further focus on design. Now, look at this. If we are going to use air, then we have to also identify what are the ambient condition, temperature, pressure, humidity. Okay. And nowadays, air is so impure, you also have to focus on how much solid and dust is present. So here, so look at the second point, atmospheric contaminants. So atmospheric contaminants, which are can be dust, hydrocarbon. You also have to see when you are designing a plant, what are the utilities like water, steam, electricity, or in other words, you directly say energy. Okay, so you have to see and cost of utilities, not just it is written here cost of energy, but nowadays water is also not very cheap. You also have to consider how much water it will consume. Okay, or how can you recycle the water so you and minimize the cost. And next point is like relative value of the products. Of course, everything moves around the economic. Relative value of the product means suppose a company is producing three products. Okay, so to maximize the profit, you have to see ki production of which product should be higher, production of which product should be lower. So that is the meaning here, relative value of the product. Okay, so that you can manage your economy. And you also have to focus on alternative operating cost. Sometimes alternative operating cases
Quantity is invariant.
so
I produce more oxygen, less nitrogen, like that.
so alternative operating cases means suppose there are two products like in this case we can produce oxygen and nitrogen, but then we have choice, should I produce more nitrogen or should I produce more oxygen, what should we do? These are all in design constants. So I'm not going to more details in machinery vendor, I'm going to further. Okay, and after considering these two, what are your ambient conditions and product requirements? We all know, we all are chemical engineers. We all know, we always do these three things. We have to create a flow sheet. We must do mass balance. We must do force balance. Okay, and we must do cold balance. Cold balance here is none. Here it is nothing, but it is just energy balance. Okay, where we will do energy balance, turbine or in a temperature circuit or a heat exchanger, we need energy balance. Pressure balance also inside our, if there is a distillation, you also have to observe how much pressure you are going to maintain. Mass balance, of course. So all these three equations will collectively produce the information about complete design or require specification of the equipment which we want to purchase. Okay, these are some basic cycling steps. These you have to remember. Okay, these are very important.
You're doing simulation also, no, sir?
Hmm.
You can mention that.
Okay, because these steps uh, are also involved in simulation. When you will do the simulation of this air nitrogen separation, अगर आप इसका फ्लो शीट बना के इसके सेपरेशन करेंगे, then you also have to remember this flow basic steps, how the feed moves in, what are the initial steps, what are the final steps. So first one is compression, because you want to separate, and if you remember, your boiling point was in minus below zero, so which means you have to first compress. Okay, you also have to clean your raw material. Okay, you also have to clean your raw material. Otherwise, water CO2 it will form below 0 degrees Celsius. As the temperature drops, they will freeze first. At the moment they will freeze, they will choke the pipelines. Okay, so the system will not work. You also have to focus on heat exchange, where you can minimize the cost. How? Okay, not to waste any, because temperature below 0 degrees Celsius, if you want to maintain, that means there will be a significant temperature change, and you don't want to waste any such low temperature streams. Okay, we don't want to allow the low temperature stream to release their heat into the atmosphere. That will be the waste of money. Okay, we have to make a cheaper product, so we need heat exchanger separation. Of course, we have to separate our basic raw materials, and right now we are considering, if you see this line, oxygen, nitrogen, and argon. Why we are considering three? Because these are the three main components in the air. Okay, heat exchange, as I have discussed, its purpose is simply to make it economical, feasible. Okay, cold production.
Warm product. You get liquid, no? You are warming to make it into gas.
So, coal production required to provide refrigeration means you can for liquid stream and losses. I am going to next slide so that you will see. Okay, these are the same steps, but are details in described in further. Like compressor, we need to compress air. We have already water CO2. Why we want to remove water CO2 from the air? The reason is simple, because they will create blockage. Hydrocarbon will be dangerous in oxygen-rich environment. Okay, because they are combustible. Okay, other impurities may cause a problem to the customer. Must also be removed by using catalyst or some foraging or any other method. Cold production. Heat exchanger can never be 100% efficient. Okay, so somehow you have to do the energy management. You have to minimize the you have to minimize the energy loss. That is the meaning of this coal production. Okay, during the day we also need to consider the cold energy required to cool down the plant from warm during startup. Now, on this slide, I would like to recall two ways how it, somehow we have to manage the energy exchange. Try to understand. We have to do the energy exchange. So either by using heat transfer, heat exchanger, that is the one way. But because air is at room temperature 25 degrees Celsius, and we have to operate below zero, so that means first somehow we have to cool the air. Okay, so naturally there is no heat exchanger we can get which can produce below 0 degrees Celsius. Try to understand, I am repeating. Naturally there is no heat exchanger present in on the earth कि वो जो 25 डिग्री सेल्सियस की एयर है उसको बिलो 0 डिग्री सेल्सियस पे पहुंचा दे. Okay, -1 near -170 degrees or -190 degrees Celsius. No, not possible. So how we do this? The heat exchangers, such a heat exchangers are not available. So we use, like here it is written JT stream. JT means आपने फर्स्ट ईयर में थर्मोडायनेमिक्स में पढ़ा होगा. If you recall, JT means Joule Thomson effect. We take advantage of Joule Thomson effect to
Sprays also.
to make the temperature below 0 degree Celsius. So how the Joule Thomson effect? I am just recalling. I hope you all remember, but I am just recalling. Whenever a gas moves from high pressure region to a low pressure region through a adiabatic channel. Adiabatic channel means when the gas is moving through a channel or a porous plug, that porous plug must be insulated. That is the meaning of adiabatic. Okay. So if the gas moves from high pressure to low pressure, what happens? Temperature decreases as well as pressure also decreases. चलिए एक एग्जांपल आपको दे रहा हूँ जो रियल लाइफ में आप सब यूज करते हैं. जैसे हम डिओडोरेंट की बॉटल ले लें, that can be seen as a Joule Thomson. There you can feel the Joule Thomson effect. LPG गैस सिलेंडर, मैं बता रहा हूँ, इसका यह मतलब नहीं है घर में जाके LPG गैस सिलेंडर का के साथ आप खिलवाड़ करने लगे. I am not suggesting that. I am just telling you. Okay, how you can feel the Joule-Thomson effect. तो जैसे LPG gas cylinder में, if you have seen sometimes, people press the pin of the cylinder by hand. If you do that, immediately you will feel very cold. How did that happen? ये कैसे हो गया? That is exactly Joule-Thomson effect. Inside the cylinder, pressure is high. Outside the cylinder, pressure is low, which is atmospheric pressure. The moment the gas comes out from material comes out from high pressure to low pressure, temperature decreases. And this is exactly the Joule-Thomson effect. अगर आपको एक्सपेरिमेंट करके देखना है, डिओड्रेंट की बोतल लीजिए, यू प्रेस इट, इनसाइड द डिओड्रेंट बॉटल द प्रेशर इज हाई. या परफ्यूम बॉटल, इफ यू वांट टू टेक, यू कैन टेक दिस, बट परफ्यूम विल बी मोर कॉस्टली. You can do the cheaper experiment with deodorant. Deodorant bottle, inside the deodorant bottle, pressure is high. Outside pressure is 1 atmosphere, very low.
Specialty chemical.
Okay, so the moment you press the deodorant knob on the top, the material will come out from high pressure to low pressure. And if you put the finger or your palm in front of the nozzle, you will see the temperature, your hand will feel cold. So which means temperature of the material has decreased. So you see the pressure, material is moving from high pressure to low pressure, temperature is also decreasing. Okay, temperature is, this is called Joule-Thomson effect, and this is exactly what we use to liquefy the gases. How? First we force the gas to move from high pressure to low pressure, so that the temperature goes below zero. Okay, and so that means we first need to put the material at a high pressure. So how we put the material in under high pressure condition? For that we use compressor. Okay, in the compressor, by using compressor, we can increase the pressure of the air. Okay, that's how first we increase the air pressure, then we cool it using Joule-Thomson effect, liquefy it. Okay, चलिए आगे बढ़ते हैं. So of course heat exchanger will be there, and there are 3 layers of heat exchanger. Means what are the material where you want heat exchanger? There you see this box here. It is like a trapezoidal. It is shown. So this is nothing but a symbol of compressor. You see, whenever आप कभी आपने गाड़ी में हवा भराया हो, whenever you have taken air for your bicycle or bike, you and if the compressor is running, if you put on your hand on running compressor, you will see compressor is producing a lot amount of heat. Okay, whenever a compressor is pulling air and putting it inside the tank become warm. So why, अगर एयर प्रेशर तो बढ़ गया, जो टैंक में the air which accumulates inside the tank, pressure increases, but temperature also increases. So why to waste the energy? So that is why around the compressor you also need a heat exchanger. Okay, to conserve energy. That is nothing. Another, if you are producing liquid oxygen, suppose at minus 180 degrees Celsius you produce a liquidized oxygen. At minus 180 degrees Celsius we produce liquid oxygen, but when I will sell the liquid oxygen to my customer or say to the hospital, temperature of the hospital is only 25 degrees Celsius. So if I sell my liquid oxygen cylinder at minus 180 degrees Celsius, जब तक वो सिलेंडर हॉस्पिटल में पहुंचेगा उसका सारा टेम्परेचर तो लॉस हो गया. So that means from liquefied oxygen also you have to extract the heat. Do not waste heat in any form. We can use minus 180 degrees Celsius oxygen just to heat up our other streams wherever you want. So heat exchanger is any other cooled waste which we are producing also must use a heat exchanger. So it is just a brief diagram to understand. So let us go further. Like I said, cools incoming air from, this is a 25 degrees Celsius temperature approximately, and it is cooling to where? Nearly minus 173 degrees Celsius. You can see here. So this is exactly what I just explained to you. So next, moving ahead is distillation. So in the distillation, how I'm just trying to explain how distillation works. Suppose first thing we need to compress. I'm restarting again. First thing you need to compress the air. When we will use the compressor, air will be compressed at higher pressure. It will be at higher pressure, but the temperature of the air also increases. We need to operate near minus 170 or minus 180 degrees Celsius. So high temperature of the air is not required. So what we will do? We put heat exchanger. ओके आप आरा खुद से सोचें यू विल क्रिएट योर ओन फ्लो शीट देन यू नीड टू पुट ए heat exchanger. That heat exchanger will remove the temperature of the air, and it will bring the temperature of the air from near around 100K. Like here it is written, air at 100K minus 170 degree Celsius. Now, as we have seen, the boiling point temperature of nitrogen, oxygen, and argon are they have differences. So we use exploit the same property, differences in boiling point, to separate the liquid. So if you check let me go back to the same slide. If you remember the boiling point, you have to remember these values, otherwise you can't. Yes, the boiling point here for the oxygen is minus 183, nitrogen is minus 1795, and argon is minus 185. You just remember that argon lies in between oxygen and nitrogen. So to cool
Closer to argon.
so if we are cooling, oxygen will be cooled early. It will become liquid first. You see, its boiling point is higher than the nitrogen, minus 183. This is negative value. So boiling point is higher. Okay. So it will cool early.
That will be liquid.
Okay. And it will become liquid early. Then the argon will become liquid, and then nitrogen. Okay. However, in reality, whenever we try to cool, ऐसा नहीं होगा कि पहले ऑक्सीजन होगी फिर नाइट्रोजन होगा. No, all three gases will cool simultaneously. Okay, there is no 100% pure operation. Try to understand. All these all three gases will cool early. Cool. But if we look at the liquid product, it will be rich in oxygen because the oxygen boiling point is higher. Okay, higher than the nitrogen. So oxygen will easily liquefy. Nitrogen will have face difficulty in liquefaction. This is what I am trying to say. The component which cannot be easily liquefied, it will be in lower concentration in the liquid product. Okay, this is how we use for separate. This is the trick we use for separation, because incoming air at 100K near minus 170. At minus 170, all our nitrogen, oxygen, argon, all three phases will be in the gas phase. So in the distillation column, we try to decrease the temperature, and we want to separate the oxygen. So let us go further. These are some design related questions. How do we supply trace to the liquid, or how? I'm not going into that right now, rich oxygen, but we have some videos for better understanding of these two questions. So directly, I'm coming directly to video for better understanding of
You can go, come down.
these two processes. These are slides, but you will face. I'm going to show you this video. and then I will explain with the help of the video so you can understand.
Check, are you able to see the video?
Just a minute.
Full screen.
Now tell me, can you see this video? Hello, everyone? Hello?
Sir, it's the lecture slide only.
Lecture slide. Okay, I'm going to share my screen.
Share screen. इसको escape minimize देखिए and then show the video.
So, up. We have to go to Google Meet. Let me tell me if you can see the video. Hello?
No, sir.
No video.
No, sir.
You are not seeing the video. So they are not seeing the video.
Sir, we are seeing your faces.
Yeah? My
Sir, we
face
are
is,
seeing your face.
camera is working, sir.
Okay. They are not able to see the video.
Hmm.
The problem is this.
Problem why? Can you see this browser? Hello? No.
No, sir.
They can't see this browser. So they can't see the video. Sir. Sir. Give me. Okay, so I'm going to share the screen.
Video, video. Where is the video? Video, please.
What happened to the video? No, different video, sir. Sir, you can't see it right now, no? Sir.
See the window.
Sir, give it to me. I can do this. Let it be this. Okay.
Entire screen. I'll get you the video from that.
No, in my our is
We have closed the PPT also.
yeah from here. It's not showing any video. ये मीट का वीडियो दिखा रहा है. Stop presentation. So,
Explain, I'll get you.
from here it cannot run. Let me see, sir. Ca- Can you see it now? Hello?
Sir, we can see the Yes, sir. slide.
Sir, we can see the slide.
Okay,
No.
it is not transferring from slide to YouTube. You have to share your screen, sir. There is no other way. So, chat window में where?
The slide me, we have nothing there.
Okay. Okay, then I'm going to give you the video link, and I'm also going to share, like, I'm giving one video link to the in the classroom. That is one, and I am going to. I'm going to. This way it can. Just now. They can see my screen.
Yes, sir.
Okay, now you can see my video, right?
Yes, sir.
Uh, just a moment. They are seeing this. Okay. So now you can see.
Yes, sir.
Okay.
Yes, sir. Yes, sir.
So first I will let the clip go, and then we will discuss it.
Tell them to observe the screen then.
Now they are not seeing us.
Now they are seeing. I don't know how to switch over between video to slide. Capture.
All right. So now
Then you
you,
can show the other video also.
I can show another video to you. It is all.
Yes. Just single.
So I'm explaining just brief.
No, you can go back to slides, sir.
No, no. This from here.
Huh? Okay.
Okay, I am just leaving those slide. I'm trying to explain this process. I'm explaining one of this video. So, oh, What?
This is the subsequent link. No.
No, this is not the link.
Come back here and click on.
So I hope you understood the first step is purification, compression, purification. These parts I hope you understand. I'm just coming to the distillation column and trying to explain. Now here you must notice that air has been cooled at to around minus 173 degrees Celsius before sending this air to the distillation column. And this has been done by Joule-Thomson effect. Okay. Now this is your distillation column, and if you look at this distillation column, it doesn't. If you look at this distillation column, it has two parts. One is upper distillation column, one is lower one. Lower one is having high pressure, that is say around 6 atmosphere or 6 bar. Now, what happens? Now, what happens to this feed? सर वो फुल स्क्रीन में कंट्रोल कर रहा है.
You pause now.
Okay, let me explain. So this is how our cooled air near about minus 173 degrees Celsius, it comes in. Now, what will happen here? The moment the temperature here is minus 173 degrees Celsius, so lighter component, which is nitrogen, that will go from top. Okay, then and in this and nitrogen here will go from top, which because oxygen will easily liquefy because it is heavier at minus 173 degrees Celsius. Oxygen and argon will easily liquefy, but nitrogen will not. So nitrogen will rise to the top. Now, what we will do with this nitrogen, we will do two things here. First, we separate this nitrogen. This is just for production. We can sell it directly. Okay, this nitrogen. And some part of the nitrogen we use further for in our operation. You see this line here, we are doing nitrogen production. We can use it for selling or something other. Another part of the nitrogen goes from top to the other part of the column. Okay, now
How much is taken and that will be by material balance.
so so now that in this column, smaller column, we have in the bottom product is mainly rich in oxygen and argon because we have separated nitrogen. Remember,
Oxygen and argon.
our oxygen and argon, because from the top we have separated non-nitrogen. Now remember one thing: no process is 100% efficient. This we cannot assume that there cannot be any nitrogen in this liquid. There may be some traces of nitrogen here. Now what we will do again? This bottom product is mainly rich in oxygen and argon, so we will separate both oxygen and argon. So what we do? We take this bottom product to the next column. Okay, we take this bottom product to the next column. Now look at the temperature here. This is a cold liquid phase. This is a liquid phase. So at minus 173 and nitrogen coming from top is having minus 177 degrees Celsius on temperature. Okay, so when this nitrogen come into contact with this is heat exchanger. Try to understand. This is just a heat exchanger. We are not mixing two stream. It is just exchanging stream. So this vapor phase nitrogen will come in contact with this liquid phase oxygen. So what will happen? Nitrogen will cool down and oxygen temperature will rise. So oxygen and argon will rise from this tube and nitrogen will rise from this tube. Now further, just a moment. You see in this channel, you can see the color of the nitrogen is changing. What it is trying to represent? They are trying to say that it is being liquefied. Temperature is dropping. How temperature is dropping? Because of this heat exchanger, and also uh, any other device like Joule, which is having Joule Thomson effect. We are cooling the
Different between the two
nitrogen.
columns.
In the second column, what we need? We need low temperature nitrogen. You can see from the top, it is a cold nitrogen which is entering from the top. Okay, some part of it then vaporizes and moves from the top. Okay, so why we put this cold nitrogen, liquid nitrogen from the top? So first we need to understand from in this column how the feed is coming. Sorry. This pipeline from the bottom column is bringing in your argon and oxygen. Okay? This pipeline is bringing in your oxygen and argon. The moment the liquid nitrogen, because here temperature is very low, so oxygen will liquefy first. Okay, if you check the boiling point difference, oxygen will easily liquefy. So what will happen? Oxygen will accumulate at the bottom of the column, and our organ will remain mainly in vapor phase, and it will accumulate here at the top. Okay. Now this liquid nitrogen is exchanging heat with this feed stream. So as a result, some part of the nitrogen will vaporize, so it will leave from the top. So from the top of the column, you will collect nitrogen because nitrogen exchanges heat, so it will come in form of vapor. From here, we will collect argon, and oxygen is easily liquefied here, so oxygen we will collect from the bottom. So if you see the color difference, I am running this. So you see this red color, they are representing to show the oxygen, and it is written here in this video, dioxygen means O2 is extracted for production. So, and if you look at this video, you can pause it. It is at the bottom, it is showing the liquid phase of the oxygen. Okay, liquid phase of the, and one important thing you must note, look at the temperature here. Where the liquid nitrogen is entering, the liquid nitrogen temperature has been brought minus 193. That's how this second column is working. If this temperature is not below this, not lower, then you cannot supply liquid nitrogen. This process will not work. Okay. So you need very cold nitrogen.
Minus, you should know.
Okay. Minus 193 degrees Celsius nitrogen.
Colder than minus 170.
Okay. And it is, but at the bottom it is higher temperature, minus 179. So from the top, temperature is lowest. Try to understand. On the top here in this column, temperature is lowest, and here temperature is highest. Okay, these are negative values, so you have to think carefully. Okay, so I hope this process is clear. So as soon as our oxygen and argon comes here, at this cold temperature, oxygen will easily liquefy, but argon will not. So oxygen will accumulate in phase as a liquid phase, and here at the bottom of the second column, argon will not accumulate, but it will leave from the middle of the column as a gas phase. So from this tube, we will see argon coming. So I am running the video a little bit ahead. So here you can see from the middle tube, the oxygen is coming out. Red color indicates here, so from this middle tube, argon is coming out. Red color indicate oxygen. So I hope you understand this flow sheet. And if you still have any query, you can call me anytime. So I'm stopping the screen sharing, coming back to my slide.
Recordings.